It's great to be back in Singapore. I believe it's my 5th or maybe even 6th visit over the last 13 years. The place is as warm as it was, as it always has been, both in terms of hospitality and in terms of weather. And I remember very well that the first time I was giving a talk here, I started off saying that I would be talking about cold atoms. And that's probably appropriate because this morning in Warsaw it was minus 20 degrees. I could almost repeat the same sentence today, but that would be exaggeration. It was only minus 10, I believe. It's a little warmer, yeah? OK, so great to be back in Singapore. And let's start with something that is familiar to everyone, this famous very first picture of the condensate from Gila from 1995 of two groups, Cornell and Wyman, guys who eventually got a Nobel Prize for this achievement together with Wolfgang Ketteler. And what we see here is a distribution of atoms, you can say in a trap, just cutting some corners. And the temperature is decreasing if you go, as we go this way. This is the lowest temperature situation. There are only about 2,000 atoms in this experiment. And for such conditions of rubidium that has been condensed, this is more or less a Gaussian of the ground state of the harmonic trap in which the atomic sample has been held. Well, that was really the beginning of the avalanche of papers and interest in the condensate, and in particular, preparation of a condensate really requires going beyond the ideal gas situation. One had to account for the collisions, for the interaction between atoms, because these collisions are necessary to thermalize the sample while the whole thing is cooled, or if you want, while some energy is taken out of this cloud, actually together with also some atoms. So if they need to collide, then the question comes to mind how to describe the fundamental interaction between two atoms in such a cold sample. And the potential that you have to assume that governs the van der Waals forces between the atoms is really irrelevant in details. Why? Because the gas cooled in these experiments is very dilute, and typical distance between the atoms is 100 or so times larger than the range of the van der Waals interaction. So there is a tendency, of course, to assume, for simplicity, that it is just a three-dimensional delta function, that it's only a contact interaction, that they really feel each other only if they come to occupy the same point in space. Now, this formula, which describes what is called Fermi pseudopotential for the contact interaction, is more complicated than just 3D delta function for interesting mathematical reason. It happens so that three-dimensional delta function added to the Laplacian, making a Schrödinger equation for two colliding particles, would constitute the Hamiltonian, which is not mathematically proper, which is not self-adjoint. This mathematical weakness of this has been noticed long time ago, actually in the 30s, and Fermi and Bright were the first to really discuss how to cure this disease. And curing this disease requires, what's going on? I pressed wrong place on the screen, sorry. So curing requires this operator d by dr times r. Then you would put wave function next to it. And with this simple trick, the Hamiltonian for this contact interaction becomes mathematically healthy. Now, if you look at this additional complication, then you can easily convince yourselves that this mathematical complication is necessary here only if the operator is about to act on the wave function which is singular at the origin, which has the singularity of 1 over r type. They are, of course, important in 3D problems, but otherwise, if there is no singularity, you can easily forget it. And that's why a lot of people forget about this correction, and yet they do not make a mistake just because they happen not to stumble upon the singular function. Then there is one important physical parameter here. There's the S-wave scattering length, and this A is the only information about the real van der Waals potential, which really we should know to use this interaction potential in actual calculations. There is a great difference between the properties of the gas for A positive and A negative, and in most cases, A is positive. So, omitting this fellow, that would be a repulsive delta, and actually rubidium or lithium, these two first elements that were condensed, both have A positive. Now, in this cooling process, a lot depends on the magnetic interactions. Magnetic field, inhomogeneous magnetic field, actually in early experiments was universally used to hold the atomic sample together. So one needed magnetic moments of atoms that are being cooled in order to really understand what's going on. However, magnetic dipole-dipole interaction, which is of course inevitable if you've got the magnetic moments in each atom, all these guys, are too small for rubidium or for sodium to really effectively compete in the cooling mechanism or in the collisions with the contact interaction. That one is a lot more important for rubidium atoms or for lithium atoms. It's not easy to compare the size of the DD interaction and the contact interaction. Of some help is what we call dipole length, proportional to the square of the magnetic moment of the atoms. You can think, okay, my scattering length, as word length indicates, of course, is a length. So there's only one object of the dimensionality length that you can form out of these magnetic parameters. But that is, of course, not enough, because what you look at, and when you look at this formula, there's also 12 pi in it, and that cannot be inferred from by dimensional analysis, of course. So there is a little bit of ambiguity in these comparisons. This particular formula, which is used by us and, well, by many groups, is based on the following argument. If we would imagine our gas held in the cube, in the box, then your magnetic dipoles, if they are placed head to tail, then they attract each other. Now, in the attractive gas, there is always a possibility of a collapse, destruction of everything, bosonova, as Cornell once termed it. Now, the same thing happens if you just have attractive van der Waals interaction, and that again defines some critical value of A. If you compare these two quantities, then you get precisely this 12 pi additionally. As I say, it's a little bit conventional, but people got used to it, and they call it dipole length. So for rubidium or for lithium, this dipole length is few percent of A here. Therefore, these guys are practically irrelevant for the collisions in the sample. Yes, magnetic moment is used for trapping, but dipole-dipole collisions are not very important. However, soon after realization of the standard rubidium or lithium condensate, there was the quest to condense gases for which atoms have sizable, much larger magnetic dipole moment. And the first heroic effort was done by Tilman Pfau, nowadays professor in Stuttgart, and the achievement was in 2005 with chromium. The experiment started while he was still some kind of a postdoc in Constance, and that's where we met. That's when I became interested in dipolar gases. So chromium has mu, which is about 6 times larger than this characteristic Bohr magneton. So in chromium, dipole-dipole interactions are 36 times stronger than in rubidium. Yeah? Still, it's only a fraction of A from the van der Waals, but already significant enough to really demonstrate some importance, so to say, for the dynamics of the gas that comes from magnetic interactions. Now, this achievement was then somehow dwarfed by two groups, one of Verleiner in Innsbruck, who was able to condense erbium. But really the best guy is dysprosium, first condensed by Benlev in Illinois, and then repeated in several labs, including again that of my colleague Tilman Pfau. So Stuttgart is now working not with chromium but with rubidium. That's the largest magnetic moment of stable element. So the race in getting stronger dipolar gases is over, except molecules where you could have electric dipoles which are zillion times stronger. Yeah? But we stay with the magnetic interactions today. Okay. So most of what I want to say today is about solitons in dipolar gases. I just took one piece of developing information about these gases. But let me start with something much better studied and much better known, namely the solitons in the contact interacting gas. So if we use the Hartree wave function for the bosonic gas, something that is routinely done, then the self-consistent equation for the universal orbital of each atom is this famous Gross-Pitaevsky equation, say in 1D. And that is known to belong to this mathematically perfect solitonic group of equations. It's typically called in mathematics nonlinear Schrödinger equation. By the way, it's also very useful in handling bright solitons of light in Kerr nonlinear media. But here we are dealing with atoms in 1D sort of geometry, and equation itself is best studied for infinite line. Now, of course, that's mathematics. Physics is slightly different. First, that's not a big deal. G unlike typically with light, G with atoms is positive, and in this case, this equation admits dark solitons, notches in the dips, yes, in the C of the gas, rather than bumps. However, life is never perfect. We never deal with atoms on infinite line. our traps are always finite. In some sense, we are always in 3D, except maybe very elongated trap, but there is always some transverse possibility of transverse dynamics. And also, almost always, also in this longitudinal direction, there is no free motion, it's rather the trapping potential. So there is certainly no translational invariance in the lab, with the exception of some very special experimental arrangements. So there are, well, as I say, life is never perfect. Mathematics is perfect, but physics is not. Okay, so how did people produce solitons in the contact interacting gas? The method that has been more or less simultaneously discovered in Hanover in Ertmer's group and at NIST in Bill Phillips' group is called phase imprinting method. And it is sketched in this thing. Imagine this is our condensate, maybe not so spherical, rather elongated, but who cares? Now we cover half of it. Actually, in the experiment, it was just a blade, and shine some light. If light is strong enough, then it amounts to creating a phase shift between left and right part of the condensate, and actually the phase shift equal exactly pi creates a dark or black soliton. That has been done, as I say, a long time ago, almost simultaneously in two places, and then the method has been developing. Klaus Zengstock, who was part of the Hanover team initially, got a position in Hamburg, and among many other things also further studied the solitonic type excitations. And I will flash one picture from his paper, I think published in 2008. He created two solitons in the elongated trap and traced its motion. As you see, these guys, of course, cannot travel with a constant speed like mathematical solitons. They are in the trap, so they oscillate. They oscillate. And there are two of these guys, so from time to time they have to collide. And as you see, nothing happens at the collision. You could ask, and that's a legitimate question, how do you trace the motion, the dynamics of such a system? Well, the answer, frank answer is, well, you have to cheat a little. Namely, each pair of points here is taken from different realization of the experiment. Because to take a picture and finding where are the solitons is also destroying the condensate. So they are trying for, say, 100 or 200 times to create at t equals 0 solitons at exactly the same position, and then they wait longer, and take picture at various times, right? And this way, you see, they can cheat just a little, but they have access to the dynamics. Important, as I wanted to say, is that when they are crossing each other, say, not much happens. Just as mathematical solitons should do, by the way. Okay? Now, let's go to the dipolar systems. We want these dipoles to be along some elongated trap, but polarized perpendicular to the axis of the trap. So in this case, what is dominant is a repulsion between such dipoles. Once again, if they are located this way, there is attraction. So actually, whatever thin is your condensate, there are always, of course, some of these dipoles that are head to tail, and they attract each other. So it's a combination of two types of interactions, nevertheless, in spite of the polarization, and assuming that your transverse confinement is sufficiently tight, you can safely say that in these two perpendicular directions, you are always just occupying a ground state of the harmonic potential. So you can assume that your wave function has two terms which are just Gaussian, and with proper phase factor, but that's not very important, are Gaussian, and the dynamics is really in the z direction. Now, if you assume this and integrate over this equation, then, of course, for this remaining phi of z, you will get equation that still looks very much like Gross-Pitaevsky equation. It's much more complicated than the original one because there's this integral character because of the action at the distance, because of the long-range forces that you have here. And what is very important, we've got some effective potential here describing this interaction, and effective potential that can be derived easily just with the help of a well-known formula, plus, again, well-known formula for the Gaussian wave functions in x and y direction. This is analytically doable, and this V effective is expressible both in position and in momentum space by known simple special functions. Special functions that Berger would know by heart. Okay. Good. So, to summarize, we've got this system built of slices, and these slices interact via this effective interaction, which is not exactly this simple 1 over r cube. It's slightly more complicated. And very important parameter here is aspect ratio, or the ratio between perpendicular size, say, of these Gaussians and the length of the trap. Okay. How does it look, this effective potential? Easy is its long tail, which of course 1 over z cubed, that is kind of trivial. But at distances which are of the order of the size of a transverse wave function, there is a steep increase. What is kind of funny is that it ends at z equals 0 with a finite value. That's okay, that's very nice. We prefer finite values than singularities. However, a trace of the singularity of 1 over r cubed at r equals 0 persists here, because this is not a full story. Plus, added to this, there is also a delta function contribution. So there's also some kind of a effective contact interaction, which is a result also of dipolar forces. Now, this should add now to the van der Waals delta function, and then we would play with what is called Feshbach resonances to change the value of the constant, this combined constant of true physical interaction and this residue of the dipolar forces. And just to emphasize our interest in the action of these long-range interactions, we just heal this delta potential entirely by assuming that Feshbach resonance was used to do so. Fine. And here is what we get. What we get is compared to the so-called Zakharov and Shabbat dark soliton of the contact interacting gas. This is now compared to several solutions that are corresponding to this one for dipolar gases. And we see that if you have very, very, very thin condensate, then there is really no difference. When lambda grows, then there are these shoulders that are appearing that are clearly distinguishing this so-called solitons from the standard nonlinear Schrödinger equation solitons. Now, the calculations here are not done really for the box. They are done for the box with the periodic boundary conditions. And if so, then the jump, which occurs here of the phase, cannot be just left alone, because then if you continue the phases, they would not match properly on the other end, so to say, where the ends meet, right? Therefore, everything is done with a phase as d-dependent, having this sign term, yes? So in other words, they are going like this, jump, and then return. What does it mean? Perhaps you remember that if you have such a quantum equation, then the phase which has a gradient is the same as saying that everything moves, because this gradient of the phase is the velocity of the gas. Yes? So unlike in the standard Zakharov-Shabat case, where for the infinite line this is a steady, stationary object, this black soliton, our dark solitons do move. Move because of this glowing phase. Okay, now we produce such a thing, but now the question is how does it propagate, whether it really deserves in any possible way the name soliton. So we created this soliton with nice little shoulders for lambda equal 10 to minus 2, and then we let the equation go in real time, and then indeed for a long time, much longer than it's shown on the picture, it stays as it should. Created right in the center, it is, created anywhere, provided we are in the co-moving frame, because as I say, if I would use a lap frame, it would not be straight line going up, it would go like this, yes? So created like this, it will last forever. The next little exercise was the situation of two solitons. I was trying to indicate something that probably most of you know, that nonlinear Schrödinger equation solitons just go through each other without any visible interaction. There is some phase shift, which I'm not going into these details here. But here, because of the long-range forces, our solitons do interact. And one can find some kind of the potential curve for these guys by creating them at well-controlled distances and probing the acceleration at the beginning, yes? That allows to compute the force, and then you integrate it once and you get a potential curve. As you see, this potential curve looks very much like a molecular interatomic potential, right? So question is this motion in this potential or elastic, or there is some inelastic aspect, inelastic feature in this motion? Okay, if we start placing our guy at A, which is above the what you would call ionization threshold, then the picture is kind of dull. Of course, they just move apart and travel on the circle, so they appear and reappear all over. Nothing interesting. What happens if I place it somewhere at B? Also something that you expect. Well, they are bouncing like this because they are, of course, below the ionization threshold. If I would run this for very long times, then I would discover something, but we had no patience to wait so long. But then we did the experiment placing these guys at C, which is very close to the ionization threshold. And lo and behold, the result was somewhat surprising. First, we've got, again, oscillations. And then these guys gained so much speed that they started doing something like this. In other words, this way we've proved that not only our solitons interact, unlike true mathematical guys, but also we've shown that they interact inelastically. To really understand what's going on, how to interpret this, we increased to some absolute values the strength of dipolar interaction, and then we produced a situation in which these these solitons collide, and in one collision gain so much speed that they go apart. What's going on here? Well, what's going on here is very similar to the situation of two electric charges which are attracting or maybe repelling each other. If they really move with some acceleration, then of course they would produce electromagnetic waves, right? And they will lose some energy. Here, corresponding are phonons, are these other important excitations of a system. And these little ripples that you see here are phonons emitted during this collision process. These guys are accelerated, so they have to radiate. Well, but if we had charges that collide and radiate, then you expect that they will be slowing down and not speeding up in the process. But we do not have bright solitons here. We have dark solitons here. And they are very often interpreted as negative mass particles. Negative mass particles, that's another story. If they lose energy, then they are faster. They are speeding up. So that's really what happens here. By the way, the theory shows that they move faster and they get shallower in the same time. Yeah? So they are graying like old guys. Yeah? They are graying. Here, this line just shows the speed of sound. And the speed of sound is what phonons are moving with. Yes? That corresponds to the speed of light for colliding charges. Okay, that allows us to study something, I would say, rather nice. We can now let our guys collide, go to this motion, and in this motion they, of course, collide twice, here and on the other end, every time they go around. So there is a lot of collisions. What happens is that at the beginning, they are graying with accelerating speed. What does it mean? Well, don't forget that our universe is closed here. So phonons, while produced, are also traveling like crazy around. And they are traveling like this. They meet these solitons very often. Again, what happens then? Then not only we've got spontaneous emission of phonons, but there's also stimulated emission of phonons, and therefore graying, which is just indicated by this vertical component, is actually accelerating, getting faster and faster. We call it super radiant phase of the evolution. However, unlike in the optical superradiance, once again, we have to remember that our phonons never escape. And as you know, like photons, they can be also absorbed. And then as time progresses, and we've got hundreds, if not thousands, of revolutions of our solitons, the equilibrium, dynamical equilibrium emerges between processes of absorption and emission of phonons, plus, as a result of such dynamical equilibrium, there is a huge fluctuation, as you see, occurring here. I don't know whether one day somebody will be able to do such experiment, but it would be just fascinating. It has, I would say, some cosmological analogies even, yeah? Okay. So, we have done some work on this contact gas solitons in the past. I will not review this because that would really take me beyond the time allocated to this talk. But I want to tell you that for these contact guys, we found out that something that Berge alluded to in his introduction, that looking at our finite temperature samples, we found that gray or dark solitons are actually present there without any phase imprinting. They are just ordinary elementary excitations of a system besides the well-known and better-known phononic excitations. So the natural question to us was whether dipolar solitons also exist in thermal equilibrium in non-zero temperature system. We had to construct so-called classical field that corresponds to non-zero temperature, and we, for a reason that is again beyond this talk, we were not using, in this case, our in-house version of classical fields. We rather used something imported from Paris using Bogoliubov excitations. Bogoliubov energies are analytically known for such a box potential, for such a ring potential. They are given by this, where this is just a Fourier transform of our interaction. This is well-known expression for the Bogoliubov relation between atomic creation and annihilation operators and operators creating and annihilating Bogoliubov excitations. Then we assume that we've got a thermal state of these excitations, this Bogoliubov excitations, and that probability distribution is easily penetrated by means of so-called metropolis algorithm. So we can actually find this set of vectors of this beta that are relevant and invert this expression, find alphas, and then find the initial value of the wave function and then let it propagate. That's in the nutshell slightly different than our version of the classical field approximation. And I have only one picture to flash. This is again the evolution in the ring cavity. This thick line is again guiding us with the speed of sound. And you easily see that there are slower fellows. Now, slower can only be solitons, so these are dark solitons. So we proved that also in the dipolar gas, there should be spontaneously created solitons, and statistics and so of that is, of course, of some interest, but I will not go into these details. Now, at this stage, we started asking what is the situation if we include the real trapping potential in this d direction. Instead of a ring, if we would assume harmonic trapping in the z direction, we just took really quite realistic parameters that are quite easily, well, not quite easily, I'm exaggerating, are available in several labs. We took very definite geometry of a trap. As you see, elongated, one frequency is to the other to 128 hertz. And here are the dark solitons that we were able to produce. This one is the Zaharov-Shabatz soliton again, and this is in the dipolar gas, again with the shoulders. So it looks like we are in business again. Here is example of, again, two solitons created now in the trap. In the trap, these guys cannot go uphill and through the window. They have to come back, so they oscillate. And if you look closer, the amplitude of oscillation is increasing, so the same phenomenon of emission of phonons appears here, and they are losing energy, very much like those in the box potential or on the ring. Okay, now then at that point we joined forces with our British colleagues, and we started looking at the oscillations of a single soliton in the harmonic trap versus the amount, the strength of the dipolar forces. And what we see is that as the strength is growing, then the period, actually the oscillation period is increasing. That is interesting. In the case of the contact interaction, this problem of oscillations of a single soliton has been solved by many authors. One of them is our favorite pair of guys, Thomas Busch and Anglin. And the result is universal. It's not really 100% accurate, but it's quite accurate, that there is universal frequency. This frequency of oscillation is the frequency of the trap divided by square root 2. Very nice result. Nice analytic result. Now what we see here is that this is not necessarily this, because everything depends on the strength of the interaction. And you know, these guys that are working in experiment with dipolar gases, they are always hunting for sizable, major effects that are due to dipolar forces. Now here we are pointing one. Okay? So this is the 3D calculation, and this frequency here in this window, as you see, as this epsilon dd, and epsilon dd is nothing else but this ADD, which I defined in the first slide here, to the standard scattering length of the short-range forces, yes? So when this fellow increases, then this guy decreases. 1 is this benchmark for the potential, for the contact interactions. As you see, there are some instability regions here and here and here, and they are because they are there, very physical, because these calculations are done really with truly 3D code. So we are really accounting for the transverse directions. We are not using any effective 1D toy. And if so, then, you know, then there is, if dipolar forces are strong enough, then there must be instability because of this head-tail situation, which is possible. Yeah? That enters instability, which is often called roton instability. I don't want to discuss this further. That's slightly, I mean, vaguely related to what Rafa was telling you. Yes, telling some of you yesterday. It's unstable. It's also unstable here. This is a regime which has been, for the contact interaction was penetrated recently, well, recently maybe 4 or 5 years ago, by Italians from Trento. It happens so that in this regime there are some snake instabilities and so-called vortex solitons, so they are not real life solitons. But there is a range where everything should be fine, and there should be really very strong dependence on the strength of the dipolar forces. Okay. Now, how much time do I have?
Another 10 minutes.
Yeah, okay. More than enough. I was telling you a little bit about some of the work that we have done with basically Gross-Petersky equation, but expanded to the dipolar forces that makes them also integral equations, so they are more interesting and slightly more difficult to solve. But over the last couple of years, we also decided to reduce the number of atoms to a very small number, and then to look a little bit about the exact solutions. And in some sense, the overture to it has been done in this well-known paper that we have written together with Berge many, many years ago, where we produced analytic solution for only 2 cold atoms in a harmonic trap, and these atoms were interacting by this contact potential. So that's a kind of the benchmark for many other theoretical papers. They try to compare things with our results, and nicely they quote us a lot. This is the most important plot of the paper. These are energy levels as a function of A0s, again, of the scattering length, as the scattering length becomes negative or positive. And of course, since we are talking about contact interaction, it's only if the relative motion of these 2 atoms is in the S state, then there is some action of the potential. Otherwise, they miss each other. Right? They are never at the same point. So all these curves are kind of interesting, but perhaps the most interesting is this one, which is below 0, which does not really have anything corresponding for ideal gas, which really describes the weakly bound molecule. And these weakly bound molecules are actually being seen and measured in many experiments, And they are especially important for something that I also do not go into detail, this so-called BEC-BCS transition. On the BEC side, where the molecules are formed, these huge molecules that are formed are beautifully described by this branch of the solution. Okay, nice. But then, together with actually Rafał, who is here, and another student, we asked ourselves, time is passing, almost 20 years, maybe 15 years at that time. It's time to do something more ambitious with two atoms, and more ambitious is to equip these two atoms with magnetic moments and look at the corresponding, if you want, corresponding problem, but with two dipolar atoms in the trap. I will not go through all this relatively complicated algebra here. I will only say that, of course, the magnetic moment for such a guy is proportional to the spin, to the total angular momentum of the atom, right? So we've got, again, without going into detail, separation of variables into relative motion and the center of mass. Of course, still our interaction, dipolar interaction, depends only on the difference between positions of these two atoms. So only the relative motion is of interest, sure, like here. And plus, the whole thing, together with the dipole-dipole forces, of course, is spherically symmetric, if we assume that the trap is spherically symmetric, what we do. If so, then the total angular momentum is a nice constant of motion. So every state can be labeled by J and Mj, yes, the projection. And the rest can be constructed using Clebsch-Gordan coefficients, stuff like this. To help this, to make it easier, I just show you that we can, of course, express this DD Hamiltonian in terms of individual spin operators and these other operators which really are raising and lowering L value of the relative motion. So this way, using the algebra of angular momentum, one can actually very easily reduce everything to sets of small number of radial equations, and those radial equations then are solved at the end numerically using shooting method, and that is more or less straightforward. I just want to flash something which corresponds to our famous graph of energy levels for contact interacting atoms. Our parameter, which is changing, is GDD or ADD, if you want, the strength of the dipolar forces. There is, of course, also contact interaction. So at GDD equals 0, we've got the energy levels of our old paper. And then we move on from these points as GDD increases. And what we see is a picture in which there is a lot of these so-called avoided crossings. And they are interesting objects to study, because if you've got such an avoided crossing, then you always what immediately comes to mind is the possibility of going through such crossing either diabatically or adiabatically, yes? Either staying on the same curve or jumping from one curve to the other. You also know that if you've got such an avoided crossing situation, then this fellow acquires, so to say, algebraic properties of this guy and this fellow of this guy. Now, these crossings are huge in energy, so they are not very maybe useful in analysis, but there are nice crossings here because these levels are very close without any dipolar interactions. So there is this narrow guys here. Now, if you look at the content, angular momentum content of these two particular energy levels, then you can check, you can convince yourselves that this blue guy starts off with a mean value of L squared practically equals 0, while the red guy already from the very beginning has some relative angular momentum and starts from 6. So it is 2 times 3, yes? L squared is always L times L plus 1. And now, if you are able to increase GDD very slowly and go on this blue fellow along this line, then here, after crossing this anti-crossing region, you will acquire properties of red. In other words, your L squared will jump to 6. So it's some kind of the variation of what's called Einstein-de Haas effect. What is Einstein-de Haas effect? Probably most of you know is if you have the spin-orbit coupling and you've got magnetic field which can polarize your spins, and then you change this magnetic field to the other direction, yes, then because of this coupling between these two parts of total angular momentum, everything, this whole body becomes to rotate, starts to rotate. Yeah? Now here I do not have any magnetic field. Everything is spherically symmetric. Geometry is spherically symmetric. And yet I'm able to pump to the state angular momentum, but it's pumping of the angular momentum together with the equal component of positive m's and negative m's. Yeah? So it's not that if you look at the system, it clearly rotates. Yeah? But if you would be able to measure L squared, you will get non-zero value. I think it's neat. It's been published some years ago, and we are quite happy. My last little thing is about roton. And again, I don't want to, of course, to repeat Rafał's talk from yesterday. I just want to stress that roton is a classic object in this cold atoms business. Is an object which is characterized by the minimum in the Bogolubov excitation spectrum. We have done, very recently, we have done work on these several atoms on the ring, in the ring geometry, polarized perpendicular to the plane of the ring. We've solved everything exactly and found a range of parameters for which van der Waals forces are attractive, and since they are like this, the dipole-dipole forces are predominantly repulsive. And in fact, I will just finish repeating one of the transparencies of Rafał's talk. In fact, we find that there are situations for which Bogolubov excitation spectrum, not here, but here and here, really deviates from what people typically know it should behave, linear, then quadratic. And our exact results actually follow this pattern. And then there are various characteristics of this particular states here, for instance, here at the minimum, that indeed display this roton character. We believe that this is the very first time that roton state has been constructed as a multi-particle state and not through the analysis of a mean field excitations. We are continuing to dig into these several atom systems, and in particular what's in the pipeline is our ongoing study of these dark dipolar solitons on the finite few atom systems. We have very preliminary results so far and nothing to report here. But on this note, let me end. And this is just a short summary of what I have said. Solitons in dipolar gas interact. Their collisions are inelastic. Also in this case, also because, as I said, we discovered this feature in the contact interacting gas. Also in this case, dark solitons exist in thermal equilibrium. Their oscillation frequency strongly depends on the strength of a dipolar interaction. That is something that probably experimenters, if they try to do such experiment, would love. And at the end, I mentioned that few dipolar atoms is a soluble problem with very rich structure, with a lot of possibilities, which are only beginning to explore. Thank you.